focusing on the AI frameworks that are available in the frameworks module. So for this chapter, you should know how to use PyTorch, which is a popular deep learning library by Meta, by Facebook. And we're gonna see how you can port a model that you have developed on your laptop, so on CPU, or maybe a model that you trained on an NVIDIA GPU. The code changes that you need to do to run the same model on Aurora. So let's start. So as I said, we have several AI frameworks available. And in this session, we will focus on PyTorch because it's one of the most popular of the Python libraries for training and do inference with neural networks. However, very similar changes and what I'm going to say will also apply to TensorFlow, for example. And you can also refer to, again, the documentation. So within the frameworks chapter of the data science inside Aurora, you can find TensorFlow documentation that will give you a lot of detail about most of what I'm going to say for TensorFlow. Okay, so focus is on Aurora, and what we're going to do is learn how to train a PyTorch model on a single GPU tile on Aurora, and then how to perform data parallel training on multiple GPUs using PyTorch distributed data parallel module. Okay, we can start by saying that Intel provides optimization libraries for improving the performance of PyTorch on Intel systems. This is called Intel extension for PyTorch. There is a similar one for TensorFlow. This comes with a lot of tricks to boost the performance on both Intel CPUs, as well as to enable the use of Intel GPUs. So you access this tool by importing the Intel extension for PyTorch library. And you should do this right after importing Torch. If you don't import, so if you don't add the statement about importing Intel extension for PyTorch, at the moment with the current version of Torch, you won't be able to see the XPU devices, which are the Aurora GPUs. This will change in the PyTorch 2.5 release that's coming up soon, but at this point, yeah, this is still required. And so, in order to follow on this hands-on session, you SSH to Aurora, input the mobile token password that you have on your phone, and then submit an interactive job, and then you can, yeah, for this time you can request 1 or 2 nodes, and so then a shell will open up on one of the compute nodes. You can load the frameworks, and then this is what I have done actually. So let me deactivate the virtual environment. So if you want to exit from the virtual environment you created, you just type deactivate. And now we're back to the frameworks environment. So as you can see, I can import Torch, and the current version is 2.3.1, and that's the current version available. So we can import the Intel extension for PyTorch and have and print some information about devices that are available. So first of all, we can just test that if we don't import the Intel extension. Okay, maybe that's different. But anyway, so it's always recommended to import the Intel extension for PyTorch, and then we can print out some information on the device. So it says that we have 12 tiles, which is the default. So if you so the default behavior is that each PyTorch device will be mapped to one Aurora tile. So as you know, each Aurora node has 6 GPUs that are also unfortunately called devices, but this is different from the PyTorch device. GPUs or cards. Each GPU is composed of 2 tiles that are called subdevices. Again, it doesn't it's not the PyTorch device here. The PyTorch device can be mapped to either a tile or a GPU, but by default, it's mapped to a single tile. So 2 tiles per 6 GPUs, we have 12 tiles on a node. And so on this node, we have, XPU's device count equals to 12. And as you can see here, if you want to get more information about the GPUs, the tiles, actually, so you can use the get device property, and you get, for example, the total memory, which is slightly above 65 gigabytes and so on. So you can change these, and you can find ways to modify how to map PyTorch devices to GPUs in the PyTorch chapter here on the Aurora documentation. It's even possible to map multiple ranks on a single tile. So we go ahead with the default, and let's see how you can, the code changes you have to do to your CPU code in order to train your PyTorch model on Aurora. So the first thing is to use the Intel extension for PyTorch, and the recommendation is to import right after you import the torch. Second set of changes is to replace any torch.CUDA that you may have in your code with torch.xpu, for example, for the device count here. Related to this, the other recommendation is to replace any CUDA or CPU when referring to like a device. So when using the .to method with xpu. And a recommendation here would be to use a device variable and just set, at the beginning of your code, device equals to CPU or CUDA or xpu if available. And then you don't have to change all of these statements. You just have the .to brackets device, and that will work without code changes. And the first recommendation is to define the device as I just said here, then move model, criterion, etc. to the device, the data as well, and then wrap both the model and optimizer with these IPEX optimize function from the IPEX Intel extension for PyTorch. And that's it. So here, there's a specific example of how to train of the code changes that you need to do to very simple PyTorch code in order to use the XPU. So just set the device to XPU, import the extension for PyTorch, and move model and criterion to the device, use the IPEX optimize. And as you load your data from the data loader, move those to the device as well. And the rest of the code stays the same. So you can find this example in in this, so I can go back to, let's go back to the Aurora part. There is an examples folder, and number 4, here you have the CPU code where we just set the seed for reproducibility, define the data set and the data loaders, define the model and the optimizer and the loss, and then just loop over 10 epochs where we go over our data set once and back propagate. So very simple. It's just a dummy model. And then you have the xview.py version, which is the one with the changes we've just seen, plus some useful thing like this one that automatically selects the device based on where you run, and some print statement. So just small additions to what I've shown. So let's go ahead and just do this. So make it executable, then load the framework. We've done this already. I should just move to that folder. So beginner guides, Aurora, examples 04. Now I have those examples. I can just run Python PyTorch xview. So while it's running, so it's printing the xview device and then looping over the 10 epochs. A very useful thing to check if what you're doing makes sense is to use the xview SMI tool. Chris already mentioned this. This is a slightly different command from that same tool. So first of all, you can SSH. I can SSH the same compute node here, and I've done this on this other shell. And I will load this xview SMI module. And so I can use this command, which allows to watch the utilization of the of a given GPU over time. So it's kind of updating every 10th of a second. So I should specify the GPU ID from 0 to 5. So I'm looking now at GPU 0. Okay, it didn't work. Let me just. Oh, okay. That's because I'm not anymore on the compute node. So let me SSH. Okay, now I should do the same. So I should repeat so it didn't work because I was kicked out from the compute node. I should now SSH back in. So okay, so here you see for device ID 0, the GPU utilization as a percentage and a lot of other useful information, power, and so on. So let me run the example again, and you should see that now the utilization is ramping up to 25 and 100% for tile 0 of GPU 1. This is because we're now using only one tile. So next, we are going to check how we can instead make use of all of the GPUs that we have on the node, all of the tiles, all of the 12 tiles. So that would require to use PyTorch DDP library and a little bit more code changes that are needed anyway for running on multiple NVIDIA GPUs, by the way. So these are very, very similar changes. If you're used to run on to use DDP on NVIDIA, that's very, very similar. The code changes are summarized as so we have to use the 1CCL communication library that allows the different GPUs to perform efficient collectives like all reduce For example, when all of the gradients computed on different data buckets by the different GPUs needs to be averaged. And then we have to initialize distributed data parallel. We have to use a distributed sampler to send different batches to the different GPUs. Each GPU should be pinned to a specific rank, and then the specifics of using DDP to sync the model across the different GPUs. And then some technical details about rescaling learning rate, for example, and making sure using epoch that we get a different data batch of data at different across the epochs. So here the green highlighted lines are either new lines or edited lines from the previous example. And this is basically, so we have to import MPI for pi to get the MPI ranks appropriately and to pin each GPU to a given rank. We import DDP and we import the torch CCL, 1CCL bindings for PyTorch. This whole thing is setting up some environment variables that DDP needs in order to coordinate all of your distributed training. This is to initialize the distributed communication, use the CCL backend. And here, each XPU device is pinned to a local rank. Here, we use the distributed sampler to for our data loader. And this is just to rescale the learning rate by the number of GPUs. Here is the common DDP call. So you pass the model to DDP so that it can be synced across the GPUs. And this is the sampler dot set epoch to make sure that each epoch will have a different set of randomized data. And at the end, you can clean up with the destroy process group. So, besides this block, which is just, reading a bunch of environment variables, and which, you need anyway when you do distributed training on CPU and NVIDIA GPUs, it's fairly straightforward. And you can run this on Aurora. There is this PyTorch ddp.py file that's basically this code that I showed above. And the command that you, so we've done everything here. The command that you should use is MPI exec. So you ask for, well, actually, let's just do, I'm not sure if we're on 201, on one node. All of the 12 tiles in this node. So process per nodes 12, and then we call the Python executable in this way.
Filippo, can you
yep.
do a little bit, bring the terminal a little bit higher, because I can't really see the bottom line of your.
That's
run clear.
Yeah. Okay. That's what I meant. Yeah, clear.
Okay.
Or just like do a couple of tabs.
Oh, okay. Yeah, the thing is, so as you can see, all of the tiles kind of device 0 it was very quick because it's much faster when you use 12 tiles.
Yeah.
But you have seen that both tiles had an utilization of close to 100%. So yeah, this is how you do data parallel training on Aurora with using PyTorch and DDP. So next, so yeah, I think maybe let me know if there is any pressing question. Otherwise, I can move.
Can I ask something? Don't we have 6 GPUs with 2 tiles each? So it's 12 tiles per node. Did I get that wrong? So why are we running at step 5? Why are we running on 24 tiles?
I think this is because in this example, I was asking
Oh, I see.
for 2 nodes.
Mhm.
I am not sure I can, I think I have 2 nodes as well. So the PBS node file contains the list of all the compute nodes that you have access to in your job. And yes, this is effectively 2 nodes. So I can also run this command here. And it should work this time on 24 tiles, so 12 on both on each node. There's a couple of warnings, but yeah, don't worry. Yeah,